All right, another big game changer. We are going to, in this video, graph the sine function and the cosine function, and we're going to pay attention to, there are lots of characteristics, but the two that we're going to pay attention to just in this video are the amplitude of the curve, amplitude of the graph, and the period of the graph. All right, so let's dive straight in. Okay, so now we started off with the definition that was only in a right triangle. Then we talked about the definition of sine and cosine on the unit circle, and now we have a third way of seeing the function, and this is the purest, truest way of seeing a function. We're going to think of the function as a set of x values on the x-axis and a set of outputs, y values, on the y-axis, which is not how we thought about it on the unit circle. The unit circle was this weird definition. Okay, we'll still use the unit circle, but we're going to be thinking of the functions differently today. All right, so here's what it is. The original sine function. So let's write this off to the side. F of x equals sine of x. So we're thinking input-output. Okay, so just for the original function, I'm only going to do this one time, and we'll go to Desmos and just kind of see where it came from. But so we're thinking in terms of the unit circle just initially. If you plug 0 in, so sine of 0 on the unit circle is 0. Sine of pi over 2, if you plug pi over 2 in, you get out 1. Sine of pi, also 0. Sine of 3 pi over 2, negative 1, and then sine of 2 pi is 0 again. Okay, so these points, these are I call these the 5 points on the original parent graph. This is kind of where the curve begins. So when you plug 0 in, you get 0 out. When you plug in pi over 2, you get out a y value of 1. So this point is important. On the original sine function, pi over 2 goes to 1. Sine of pi goes to 0. Sine of 3 pi over 2, that's my x value. 3 pi over 2 goes to negative 1. So here's negative 1. And then 2 pi goes to 0. So I really want you to think of the sine function. One full wave of the sine function when you actually graph it like a curve. Like we graph quadratics and exponentials and rational functions and radical functions. This is the graph of the sine wave function, the sine function. Okay, so we're just looking at one wave of it. And we can go in the opposite direction and find some values as well. But for the sake of this, I want you guys to see that the domain of the sine function is all real numbers. You can plug any number you want and you'll get all real numbers, or like we've written in the past, negative infinity to infinity. So sine, you can plug in 0, you can plug in negative pi, you can plug in negative 2 pi, negative 3 pi, negative 10,000 pi. You can plug in pi, 2 pi, and you can continue. So really this curve that we see here is nice and smooth, and it continues forever in both directions. Okay, so there really are arrows understood there even when we won't graph them. But it is important to see that the range of the sine function, it goes up to 1. That's as high as it ever goes. It's the maximum value. And it goes down to negative 1, and it just bounces back and forth. It just oscillates back and forth. So the range is negative 1 to 1, or we say that all of the outputs y are between negative 1 and 1, or we could even write using function notation, f of x, the output is between negative 1, positive 1. Okay? All right, so let me go to another slide. Odd function, that's just a quick recap. Let me just remind you how to think of odd functions, and we touched on this in our last video, but let me just recap. So let's look at pi over 2 and negative pi over 2 on the curve. So pi over 2, sine of pi over 2. So let's kind of work this out. We're plugging pi over 2 into the function. F of pi over 2, sine of pi over 2 is 1. We already know that. F of negative pi over 2, sine of negative pi over 2 is negative 1. Okay, so just to recap when we saw this in our last video. Odd, numerically, if we're going to look at an algebraic or numerical way to kind of think about it, if you plug opposites in, we get opposites out. So if you plug in positive pi over 2 on the graph, you get positive 1. If you plug in negative pi over 2, you get negative 1. And if you just look at this curve right here, it actually has symmetry about the origins. It's symmetric with respect to the origin, which actually means it has 180 degree rotational symmetry. So if you literally take this kind of S shape and you rotate it 180 degrees about the origin, this point is going to come over here, and then this point would rotate over there. So odd functions have this negatives, opposites in, opposites out feature, but graphically they have 180 degree rotational symmetry, which is called symmetry about the origin, or symmetry with respect to the origin. Okay. All right, so we know the domain. The domain is all real numbers. You can plug any number in. Those are my inputs. The inputs can be any real number. The outputs, the range, is only numbers between -1 and 1. The curve never goes above 1 and never goes below -1. And then we've kind of reviewed what it means to be an odd function. Okay. Now this function is what's called a periodic function. Now you don't have to know that it's a periodic function, but this function does have a period, meaning if it starts at 0 and you move until you get to 2 pi, which of course that's a distance of 2 pi, you have an actual wave, one full complete wave of the curve. Meaning after 2 pi, you just get a replica. You get another wave that looks exactly the same. So if you look over here, this wave, which has a length of 2 pi, is just a replica of this part. So the original period, which is the length of the wave, is 2 pi. So you need to know that the original sine function has a period, a wavelength of 2 pi. All right. The x-intercepts are kind of nice. You have an x-intercept at 0. You have an x-intercept at negative pi. So here's negative pi over 2, negative pi, negative 3 pi over 2, and this is negative 2 pi. So you have an x-intercept at negative 2 pi. You have an x-intercept at negative pi, 0, pi, and 2 pi. Okay, so that's kind of nice to see that pattern, and that will continue forever. So 3 pi, 4 pi, 5 pi, x-intercepts forever. Now, a function can only touch the y-axis once. Remember, if a curve moves across the y-axis and comes back, something like this, if it touches more than once, it's not a function, right? It does not pass that vertical line test. So the y-intercept is, the one and only y-intercept is 0. Okay? So it's just nice to see these characteristics. Okay? So your maximum value is 1, and so you have a maximum value here. At an x value of pi over 2, the maximum value is 1. Over here, negative 3 pi over 2, you have another max value of 1. And then this is important. It's nice for you to know that from max to max is a full period. That's a distance of 2 pi. So numerically, we're going to kind of see that if you start at pi over 2 and you subtract 2 pi, you'll be at this x value. Or if you take this x value and you add 2 pi, you'll be at this x value. So if you want to find your next maximum value, you would take pi over 2, you would add 2 pi, and you would get a point that we can't see on this graph. So just to kind of say that a different way, if you start at pi over 2 and you add 2 pi, you get the next max, okay? And then you add 2 pi over 2, and so on and so on. So if you move 2 pi down the line along the x-axis, you're going to keep bumping into a maximum, and so on. And similarly, you have minimum value. The minimum value is -1. And you have a minimum value at 3 pi over 2. So it's important to know initially 1, 2, 3, 4, 5 points on the original sine function. That's what I need you to know, okay? When you leave this video today, you know the original sine function looks like boom, 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 bang, pow, like this. That's one wave, one curve, one period of the graph, and you would be able to label the coordinates of those 5 points as x values and as y values. You just need to know that, and then we'll use that information to manipulate the function when we actually transform it. One last thing, which is going to be in detail in our next video, is that the midline is the line that cuts straight through the middle of the wave. So initially, the midline is just the x-axis, which is the line y equals 0. It's just a horizontal line, okay? Now, that's going to be really easy to manipulate. If I were to take this function and just add 5, so if I were to take the original function, so if I were to take f of x equals sine of x and just add 5, that would literally just take this curve and move everything you see up 5 spaces. Well, now the midline, instead of being y equals 0, would be y equals 5. So once again, I'm getting ahead of myself, but that's important. Okay, and just in case you're wondering over here, this is my window. If I were in a graphing calculator, my window starts at -2 pi and goes over to 2 pi. So this is my interval of x values that we can see in this diagram. The y values, the actual height of the window, not the curve, just the window, is -4 to 4. Okay, so don't confuse this with the actual range of the function. All right. So that is everything we need to know. That's sine. Everything you need to know about the characteristics of the original sine wave function. So now let's look at cosine, and we spent a lot of time talking about sine. We won't spend as much time on cosine because so many similarities and a couple differences we'll focus on. Okay, so let's look at cosine. Now cosine is a little bit different. You notice the first thing you notice is that it starts up at 1 on the y-axis. So the y-intercept is 1, and the reason is cosine of 0, when I plug 0 into this cosine function, cosine at 0 is actually 1. So the first point on my graph is 1. Cosine at pi over 2. So when you plug pi over 2 into the cosine function, cosine of pi over 2 is 0. Cosine at pi, when you plug pi in, cosine is -1. Cosine at 3 pi over 2 is 0, and cosine at 2 pi is back to 1. So the 5 points that I need you to really know on the cosine function, on the original graph of the cosine function. This is the parent graph. Once again, this is the parent, mom and dad of all cosine functions, is point, 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 point. And my students notice, every year, students of mine will say it looks like a V before you fill in the curve. So just make sure you build the curve like this. And of course it would continue in both directions. But those are the important values, so we still have 0 on the x-axis, pi over 2, pi, 3 pi over 2, and 2 pi. So you'll see those same values over and over. That's negative 1. That's positive 1. Woo. And that's negative 1. So kind of where you start determines where all the other points fall in. Same domain is all real numbers. You can plug any number you want into the cosine function. The range, the y values, the outputs will always be between negative 1 and 1, lowest all the way up to the highest, or you can also say all y values between negative 1 and 1. So same domain, same range. Now we have an even function. So just to kind of remind you, so let's look at pi. Just focus in on pi just for the sake of kind of reminding ourselves what it means to be even from our last video. If you plug in pi, you get negative 1. If you plug in negative pi, you still get negative 1. So remember, an even function means if you plug opposites in, you get the same output. Okay? Now, graphically, that means there's symmetry with respect to the y-axis. So if I plug in, for example, if I plug in pi over, let's say pi over 3, I get out 1/2. If I plug in negative pi over 3, I still get out 1/2. You have symmetry. You have a mirror. So every point on the right side of the y-axis has a mirror on the left side. You have symmetry with respect to the y-axis, which numerically makes sense. For every pair of opposites, you have the same y value, same output. So numerically, opposites in, same output. That's what it means to be even. Okay, now just like with the sine wave function, we start here and we end there, and that distance, just like before, is 2 pi, so we have a period of 2 pi. Okay, so the sine wave function and the cosine function, both of them, you'll hear me say sine, cosine, you'll hear me say sine wave, cosine wave, same thing. They have a period of 2 pi. Okay, the x-intercepts are a little bit different. Now the x-intercepts are at pi over 2, 3 pi over 2, etc. 5 pi over 2, 7 pi over 2. So we have this pi over 2, 3 pi over 2. Slightly different pattern. Negative pi over 2. Because it's an even function, if 3 pi over 2 goes to 0, then negative 3 pi over 2 goes to 0. So that even quality for a cosine function, it's useful. All right, for every point you have over here, you have a mirror on the side of the other side of the y axis. So that's nice. Our one and only y-intercept once again is at 1. So we got that. Our maximum value is 1, but now it's at 0. It happens at 2 pi, which is a nice pattern. 0, 2 pi, 4 pi, 6 pi, and on forever. So the maximum values happen at those x values. The minimum values are kind of nice as well. So the minimum values happen at pi, and then 2 pi later at 3 pi, 5 pi. So the max and minimum values are kind of easy to find with the cosine function. And then it has the same midline. The original midline is the line y equals 0, which is a horizontal line. Okay, same window on the graph. Okay, so just to quickly take us back, for now, it's really important for you to know that sine, boom, that's 2 pi, that's 0, that has a height of 1, that has a height of negative 1. So you're kind of living there right now. That's for sine. And then for cosine, similarly, you start up here, and you make what a lot of my students, 1, 2, 3, 4, a lot of my students say it looks like a V at first, but then when you draw the curve, you see it doesn't really look like a V. Okay, and Desmos is going to help us out in a minute. But for now, sine, that's really important. Cosine, once again, that's 2 pi, 0, 0, pi, 2 pi. So we're labeling the x-axis from 0 to 2 pi, 0 to 2 pi, and just filling in a few points. That's going to help us in a minute when we start doing some examples. Okay, so that's original sine of x, original cosine of x, the parent graphs. Now, for the transformations that we don't call transformations anymore. So when you find characteristics of sine functions, the characteristics look like transformations. Remember, when we multiply a function by a number, that transforms the graph. Well, now we're going to call that the amplitude of the graph. So the amplitude is going to be found by looking at the leading coefficient. Okay, and that's going to change the actual height of the curve, which we kind of already know that. If you multiply a function by 5, it's going to make it taller. Well, the amplitude is really like the height of the wave. It's the distance from the midline to the actual top of the wave. Okay, so we'll do an example of that in a minute. So that's what it is. Now, if I give you the equation, then you just call the amplitude what it is. If A is 5, the amplitude is 5. That's easy. But if I give you a graph and you do not have the equation, this is how you would actually find the value for A. Okay? So A is either going to jump out of the equation and be easy to find, or you actually have to use this formula to find it if you're given a graph, but we'll see that in the future. So you kind of have this. We'll kind of see the details of that later. So the only two we're really focusing on in this video are the amplitude, which is the leading coefficient, that number in front, A, and then B, the coefficient of x. So we're focusing on A and B today. The period of the function initially is 2 pi, but if you take 2 pi and divide by that coefficient of x, B, the absolute value, then this will be your new period of the graph. And we're going to see numerically what that actually means. Okay, so initially one wave had a distance of 2 pi. But the length of the wave, called the period, will change. It's dependent on that B value. Now, phase shift is going to shift my graph left and right. That's the hardest of them all. We'll do that in our next video. So I just want to let you know that that plus C, opposite of C, remember, it's always the opposite of what it seems. And when you add 5, you're thinking, oh, that's to the right 5, but it's not. It's to the left. And it's not going to be to the left C. It's going to be left or right C over B, change the sign. So you can see what I'm saying. There's a lot going on numerically when you find the phase shift. So we'll spend some time on the phase shift. That's, in my opinion, the hardest of these 4 characteristics to find and then really understand numerically. And then the midline's the easiest. So the number on the outside, D, whatever you add to the function. So I think of this as the actual function, right? You would find sine of something, bx plus c, multiply by a, and then you would add D last. So if you add 6 last, then the whole curve is going to move up 6 spaces. So now the line is going to be y equals 6, for example. So that's going to be, the midline is going to 100% depend on shifting the graph up or down that D value. So midline, easy. We'll do that in our next video. Phase shift, not very easy, but we'll sort it out in our next video. Today we're focusing on the height of the graph, really easy to find. The period of the graph, really easy to find, a little bit trickier to conceptualize. All right, so let's do some examples. So let's start with just finding the amplitude and the period. We're not graphing, just finding those values to make sure we work out the details. I don't mean to insult your intelligence, because you're going to be like, why are we doing this? It's easy. I understand. But it's good to do it and before we get into the graph. Okay, so I know that A in this problem, A is 1/2, and I know that B is understood to be 1, the coefficient of x. Okay, so the amplitude is the absolute value of A. the absolute value of 1/2 is 1/2. Okay, what does that look like on the graph? We'll find it in a minute. We'll kind of do some examples in a minute. The period is always 2 pi over the absolute value of b. So 2 pi over the absolute value of 1, which is just 1, which is just 2 pi. All right. Believe it or not, when b is understood to be 1 and c here is understood to be plus 0, people don't like that. It's almost like we do basic problems and we come back to where b and c are 1s and 0s and people freak out. I remember, it's the same in algebra or algebra 2 or any other class where you're used to seeing a number and all of a sudden it's not there, and it can cause confusion. So as basic as this seems, be careful as we kind of move into the future with that. All right, next problem. Now we have a cosine function. So sine and cosine, that's all right. They have the same a for amplitude. They have the same b, which will help me find my period. So the amplitude is the absolute value of a, absolute value of -3, which is 3. So the height of my wave is going to be called 3 from the midline to the max value. So we'll see how to graph that in a minute. And now the period, and here's where you see the relationship between b and the period, like numerically what's going on. 2 pi over the absolute value of 2 is 2 pi over 2, which is pi. So here's what happened. We took the original curve, which had a period of 2 pi, and when you multiply x by 2, that actually shrinks the period. So now instead of it going up, down, up on the way to pi, it's going to go up, down, up, and only make it to pi. So here's what's crazy. And it's really not that bad, and it'll make a lot more sense in physics when you start actually using this application. Sine waves, any wave is going to be modeled using a sine or cosine function, so it's pretty cool. So when you double the x value, you're cutting the period in half. So there's a relationship. When you double x, you cut the period in half. But what you actually do is, so if you look at my new wave, it's the frequency, how often it hits the x-axis, is now doubled. So there's this inverse relationship between period and what's called frequency of the wave. So I'll think of it like this. If you double x, you're doubling the frequency of the wave. You're making it more frequent. You're making it go up and down more often, but you're making the period smaller. So and if you make it longer, it's less frequent. So 2 is going to make it more frequent, which is going to make the period smaller, which is why we're dividing by that number. So anytime you take a value, the original period, and divide by the coefficient, that's going to actually compress the curve. So the curve was long, and now it got compressed, and you can compress it even more. And every time you compress it, you make it more frequent. Okay, so there's that inverse relationship. So it's kind of weird that as b gets larger, the period gets smaller, but if you think of it in terms of frequency, it makes sense. All right, let's do another one. Another one where we see kind of the relationship between b and the period. Okay, so the amplitude, absolute value of a, absolute value of -2, which means the height of the wave is 2. My period is going to be 2 pi over b, absolute value. Now here's where you have to be careful. X over 3 is understood to be 1/3 x. Okay, and a lot of textbooks will write 1/3 x, and some will write x over 3, but you need to know that b is understood to be 1/3. So this is 2 pi over 1/3, which means instead of dividing by 1/3, you're multiplying by 3. Okay, so if b is 1/3, the period is tripled. So now, if you were to graph the original sine function, there's 2 pi. Now, instead of going from 0 to 2 pi with one wavelength, it's going to go 2 pi. There's 6 pi. Now it's going to go all the way to 6 pi, one wavelength. Okay, and we'll see how to plot those points in a few minutes. Yeah. All right, example 4. The amplitude is the absolute value of A, absolute value of 3, which is 3. The period of the graph, 2 pi over -2, the absolute value, which gives me a period of pi. So whether it's -2 or +2, that's going to do some reflecting, but that's not going to change the period. So if this were 2x or -2x, we would have the same absolute value, therefore the same period. All right, so let's actually get into the graphing. Okay, so now, examples 1 through 4 was a lot of concept. This is what it means. This is what happens to the period. It doubles or it gets cut in half. Now I'm going to show you what to actually do to make the graph quickly. So I'm going to show, so instead of talking about the concept, I'm going to say, here's what you do. And then over the next 2 videos or so, we'll bridge those two, because you can do something and have no idea why it works. And you can understand what something is and not know how to do it. So we're going to do both of those kind of separately at first and then bridge them together. Here goes. Let's find the amplitude. So the amplitude is 4. Got it. Now, b is 1, right? So the period doesn't change. So 2 pi over 1 understood is just 2 pi. So here's the nice thing. I know that the period doesn't change. So I'm going to have the same sine. It goes up, it comes down. It goes down, it comes up. That's 2 pi. That's pi. That's 0. Right? Now, I will say this. When the period changes, right now, if the period's just 2 pi for sine, then I'm good to go. Okay? I'm just 0, pi, and 2 pi. You'll see that change in a minute. So at this point, we are still all concept. Now, the original sine function went up to 1, and then came back down, and then came down to -1 and went here. But when the amplitude is 4, that means the height between the midline, it was only a height of 1, now it's a height of 4. So the curve's going to go up to 4, back down, down to -4, and back up. That is one full period. So just to be clear, the period is still 2 pi, no change. We're going to deal with the change in period in just a minute, but not yet. And then 4 tells me how high how high that point needs to go. Now, here's what's cool. You're like, where did you get those points from? I can show you in Desmos. So in Desmos, this is my original sine function, right? I have my kind of 5 points here. I can uncheck them or check them. And the cool thing about Desmos is it knows this is a trig function, so these are exact values. So these 5 points that I'm tapping are the original sine wave function. But if I put that 4 in front, let me bring that down, kind of get it back similar to where it was. So now we see we still have 0, pi, and 2 pi. So my x-intercepts don't change, but the function is now going up to 4 and down to -4, and back up. So now here is one full period. So the cool thing is that if you are learning the tricks that I'm going to show you, you can take those tricks that I'm showing you and just play around in Desmos and make sure things work out initially. I would only use Desmos initially to check your work. you want to kind of not lean too heavily on Desmos, because once again, once we're in class, you've done all the kind of discovery stuff in Delta Math, which you'll see. There are actually discovery modules I'm going to assign, and then you have Desmos. But if this were a quiz or a test in class, you'll be expected to have work out those details prior to the test. All right, so next example. Now this is one where we're going to finally see how do I take the period and use the period to find the new points, because the points are no longer in the same place they originally were. Here's the trick. Okay, amplitude, pretty easy. So amplitude is just 3. So I know the curve's going to go up to 3, hit the x-axis, come back down, go down to -3, and then back up. So I'm good with amplitude. Amplitude's not the issue ever. Amplitude is easy to deal with. But now the number, think of this as sine of 2x. So here's the trick, and you're going to see me do this in this video and the next. Take whatever what's called the argument. So when you see this function, so I'm going to generalize it so you know exactly what I mean by the argument. Because remember, we're going to have C and D in there soon. The argument is the input. You're plugging a number into the sine function, and that number is bx plus c. Now in this problem, it's only the 2x. But in general, it's bx plus c. Here's what you do with every single problem, no matter what. You take the argument, bx plus c, and you position it between 2 pi and 0. Remember now, the original period is you start at 0, end at 2 pi, and you plug in a bunch of stuff in between to kind of find some points. So you will always do this, and you'll see what I mean. So watch this. If you're trying to graph, so you would position the argument of 2x between 2 pi and between 0. And then you solve an inequality. So my hope is that you've solved complex inequalities in the past, but if you haven't, it's just like solving 2 inequalities at the same time. So you're trying to get x by itself. So to get x by itself, you divide by 2. Whatever you do in the middle, you have to do in the margins. So you divide all of the values by 2, and now you have 0 is less than or equal to x is less than or equal to pi. So here's what this means. This means where the original curve went from 0 to 2 pi for my x values, now my x values are going to have a period from 0 to pi. So now I'm going to actually label this from 0 to pi. Now this is pi over 2. Okay, now here's where it gets tricky. What's half of pi over 2? Pi over 4. So we're going to start doing a lot of fractions. So you go 0, pi over 4, pi over 2, and this if you remember, this is kind of on the unit circle. So 0, pi over 4, pi over 2, 3 pi over 4, pi. And then what you do is you take those 1, 2, 3 x-intercepts. Those are your 3 x-intercepts now, and because it's positive 3, you go up to 3, come back down, go down to -3, come back up. It was originally from 0 to 2 pi. That 2 changed everything now. So once again, my period, so just to be clear, my period is 2 pi over the absolute value of b, 2 pi over 2, which is pi. So we know my period is from 0 to pi, which is pi. And okay, so now here's the nice thing, and I'll do this with each problem. Now I want to go in and type this in Desmos and just make sure that those really are my 5 values. So pi over 3 should go up to 3. So when I tap this point in Desmos, it should say pi over 4, comma 3. Okay? So in Desmos, I have 3 sine 2x. So let's check our points. Okay, so that's that one. Pi over 2 and pi, so that's my 1 period. Yes, pi over 4, 3 comes down. 3 pi over 4, negative 3 comes back up. So there is, once again, my one full period of the graph. And you can graph more than one period, but you only have to graph that one period. So you could, continue this and plot another full graph. It really depends on the teacher. I'm focusing on one period with 5 exact points, and that's kind of my standard, and everyone kind of has a different standard. Okay, so let's try another one. Bloop. So now we're looking at cosine. So just to remind you, cosine initially was here. And I'll erase this, but I just want to remind you, cosine was my V shape, where the curve did this, 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 and it continues in both directions. But it starts up at 1, and it ends at 1, and that's 2 pi is my period. So I'm going to use that same pattern with this problem that I used with the last. Remember, this is how to do it. Why does it work numerically? We'll bridge those gaps as we go, but for today it's just, how do I quickly plot these functions using a pattern, and then we'll kind of verify in Desmos. Okay, so my amplitude is going to be 2. So instead of starting at 1, going down and then back up, I'm actually going to start at 2, go down to negative 2, and come back up. So my V is going to be a little bit longer. So that's my amplitude of 2. Now, once again, I'm going to put the argument. I'm always going to put whatever this input of cosine is between 0 and 2 pi. No matter what, without exception. Always and forever will I do this. And now, to get x by itself, the opposite of dividing by 2 is I'm going to multiply all parts of this inequality by 2. So 0 times 2 is 0. X divided by 2 times 2 is x. 2 pi times 2 is 4 pi. So now this tells me, okay, why it tells me that, we'll spend some time with it, but this tells me that my period is from 0 to 4 pi or 4 pi. Now let's find our period, just to kind of make sure that this and this are in alignment, and they are. So remember, my coefficient, x over 2 is 1/2 x, so 2 pi over the absolute value of, so 2 pi over the absolute value of b, which is 1/2. So that gives me 2 pi times the reciprocal, which is 2, which is 4 pi. So here's how that changes everything. Now, if I'm just going to graph one full period, I'm going to start at 0 and I'm going to end at 4 pi. So I'm actually making each one of those portions or intervals of the x-axis larger. So half of 4 pi, 2 pi. Half of 2 pi is pi. So I have 1 pi, 2 pi, 3 pi, 4 pi. Labeling the x-axis, like any process, is going to, it's going to take a little bit of time. So cosine, remember, was originally up at 1, but the 2 means we start up at 2 on the y-axis, and then I go down, make my v, down, make my v, come back up, come back up. This is my one full period of the cosine curve, which if I want to extend it, I can. Okay, so here's a point, here's a point, here's a point, here's a point, just so I can kind of see the actual curve of it, the wave of it. So there it is. Now, let's verify. Let's verify that we actually have an x-intercept at pi, and that we actually have an x-intercept at 3 pi, a max at 0, which is 2, and a max at 4 pi, which is also 2. And let's just verify that at 2 pi, we have a minimum of -2. I just want to verify my 5 points. So let's go to Desmos. Now, I did not change the graph from my last problem, so we actually now have to bring that in a little bit because we expanded. Remember, when you divide x by a number, you actually make the period much longer. So let's verify. Oops. So we see the point 0,2, which is right. This point should be, yep, pi and 3 pi. We have an x-intercept. 2 pi should send me down to -2, which it does. And then at 4 pi we see 2. So we see, once again, let me tap that, we see our 1 full period of the curve, which you can zoom out and see that this thing, once again, the domain is -infinity to +infinity, and the range is -2 up to +2. It doesn't go above that. Okay, so we have our graph. All right, examples 8 and 9 will go fast, but we've got to be careful, so I'm going to draw your attention to where to be careful. All right, so amplitude is going to be 3, so easy peasy. So we're going to be up at 3, down at -3. Cosine means I do a V, so I'm going to go ahead and draw my V. So I'll start up at the top, come down. Okay, and just to kind of give you a heads up, if this were a -3, that V would be reflected, and instead of starting up at 3, you would actually start down at -3, but we'll see an example like that in a minute. Now, once again, I'm going to go ahead and find my period first. It's going to be 2 pi over the absolute value of B. And this one's going to be weird. B in this case is pi, so you wind up with 2 pi over pi, which is 2. So here's what's cool. My period is going to start at 0 and go all the way to 2. But I'm going to come back over here and do this part. Okay? Which right now you're like, I remember seeing this and being like, why do we have to do this when it's just go from 0 to 2? Because later on you're going to have plus or minus c, and that's going to make this extremely helpful. Not just helpful, but you're not going to always start at 0. Because this curve has no plus or minus inside the argument, you're starting at 0. But when you have plus a number or minus a number inside the argument, you're no longer starting at 0. So it's going to be a lot more challenging. It's easy to start at 0 and go 2 spaces to the right, which takes me at 2. It's much more difficult to start at -pi/3 and add 2. What's -pi/3 plus 2? I have no idea, and that's what this process is going to help me make sense of. So, if you think this is extra right now, it is. But in our next video, it won't. It'll actually simplify the process. Okay, so I want to get x by itself. I'm going to divide everything by b, which in this case is pi. So whatever is in front of x, you're going to divide it out. 0 divided by pi is 0. We're left with x, which is what I want. I always want x by itself. I'm never done with this process until x is by itself. 2 pi divided by pi is 2. So once again, this tells me to start at 0, end at 2, and that's a distance of 2. Okay? Which I've already done. I already see that from 0 to 2. So now I'm up at 3. Come down. Sketch, 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 sketch. If this is 2, then halfway is 1. You can use decimals or fractions. I'm going to use 1.5. You can use 3/2, which is preferred by most professors or teachers or instructors, 1/2. Half of 1 is 1/2 preferred, or you can write 0.5, or that's it. All right, so once again, let's go to Desmos and make sure that if the amplitude is 3 and b is pi, that my curve will start at 3, up at 3 on the y-axis. It will come down and end over at 2, up at 3, 1 down at -3, and let's just kind of verify. And there it is. That looks crazy. So let me zoom in like I did before. Okay. So here's what we have. Ooh, if I zoom in, it's going to tweak too much of it. So let's just check those points. So 0 goes to 3. Then we're down at 1/2, 0. 1, -3. 1.5, 0. And 2. So really my period is from 0 to 2, but normally we're in terms of pi, which is why this seems so frequent, right? Remember, when you divide, when you multiply by pi, that's going to make it much more frequent, which is why you have a whole lot more there. The last one, and I notice I have a negative a value, so that's going to mean something. So let's look and see what happens. So my amplitude, absolute value of a, absolute value of -2, which is 2. So the height of my function from the midline to the maximum value is 2. All right, my period. So my period is going to be 2 pi over 1/2, which is 4 pi again. So now I'm going to start at 0, and I'm going to 4 pi, which means between 0 and 4 pi, I should see one full period of my graph. And I just want to remind you, we're not always going to start the graph at the input of 0. That's going to be trickier in our next video, but we'll get there. So I'm going to set the argument 1/2 x between 0 and 2 pi. Once again, this process will seem a lot more relevant in our next video. To get rid of 1/2, I need to multiply by 2. So therefore, I do that in all 3 parts of the inequality. 0 times 2 is 0. We get 0 here. That won't happen next time. 1/2 times 2 is 1, so we have 1x. And then 2 pi times 2 is 4 pi. So I do want to live between 0 and 4 pi to see one full wave of my curve. Now here's where we need to be careful. Normally, the sine wave function will start at 0 and have it, so we have our x-intercepts. All right, and the curve usually goes up to whatever the absolute value of, usually it goes up to 2, back down. All right, that's normally what our sine wave function does. But because of the -2, that's going to reflect over the x-axis. So because of the negative, I'm going to go down, up, up, down. Okay? So 4 pi means this is 2 pi, means this is 3 pi, means this is pi. And we've already got our label of 2. We've already got our label of -2. So the key thing is 5 values are labeled on the x-axis and 2 values, really 3, 0, on the y-axis. You're going to hear me say that over and over. 5 values on the x-axis, 3 values on the y-axis. That's what I'm looking for when I start grading these handwritten graphs. And we are almost done. Let's just do a quick verification in Desmos, and we will wrap it up. Let's verify. Sure enough, we start at 0, and instead of going up, we're going down. Pi, 2 pi, 3 pi, 4 pi, down to -2, up to +2. So everything looks good. And remember, you can always graph more if you choose. So you could always go in the opposite direction and go ahead and finish up that curve. You do not have to. All right, one full period is all I need. Some teachers say 2 or use every portion of the grid, but you don't have to. All right, so my hope is you know the characteristics of sine and cosine, the original characteristics, and you now know how the amplitude affects the graph, how the period affects the graph, and then how you can use those 2 characteristics to make a rough sketch. All right, guys, until the next video where we get into midline and phase shift.